Hey guys, this is Jessie. This is a quick video to help you with Lab 6. I've gotten some feedback in past semesters that this one can be a little intense, so I want to provide you some extra guidance because it shouldn't be that bad. My recommendation is that you start with activity 2, tie your balloons together, take some pictures of them, and just get a really good spatial idea of what those electron orbitals look like and how their natural geometries are kind of forced when they're taking up so much space. Okay, the difference between activity 2 and what we do really in 1 and 3 is that we're looking at the atoms and how the atoms fit together, where in 2 we're looking at the electron clouds that are around there. Okay, these are the atoms and their individual bonds. Activities 1 and 3 and 4 really all kind of fit together on these on these data sheet tables. I'll fill out one for you. The idea, you actually have to pick 3 molecules from this column, 3 molecules from this column, and 3 from this column, and you have to do 9 total. So once you get going though, it shouldn't be too bad. I'm going to do ammonia, which is NH3 right here, part of group 2. I think ammonia is a good one because it has a lone pair on it, and that gives us a lot of good different things to look at. So the chemical formula, NH3, and I'm just gonna do my dot diagrams, figure out how they fit together. Ammonia has 5 valence electrons. That'll be 3 individual ones and a lone pair. So my hydrogens, which each have 1, are gonna fit on here and complete these bonds for nitrogen. And like I said, you do end up with this 1 lone pair. So once you know how many domains you have around your central atom and your lone pair counts as a domain, 1, 2, 3, 4, I can skip over to this table. I just show you that 4 domains. And I can see what my geometry is going to be like. So I have 4 bonds around my central atom. Here's an example of one that has 4 actual bonds. Now when I just subtract one of the bonds and replace it with a lone pair, so imagine this is my lone pair up here, then it becomes trigonal pyramidal. And that actually shrinks this bond angle, you can see, from 109.5 degrees to 107 degrees. And that's because those lone pairs are taking up a lot of space. They're pushing everything down around them. So that's giving you your other information that you need. How many lone pairs? We have 1. The geometry is trigonal pyramidal. The bond angle of 107 degrees. The line drawing is just my lone pair up here, and they're wanting to see the dash lines that indicate it's going backwards into the page, and the wedge line that shows it's coming up out of the page. So I have a 3D representation. The number of electrons, oh no, I just lost my pencil. Here we go. Number of electrons are how many I have total, which is 3 from the hydrogens plus 5 from the nitrogen is 8. And this is actually the Lewis structure. I've drawn the dots, or the Lewis structure. The line drawing is the 3D representation. I'm going to go ahead and show you it in the model. So all I did was select the right central atom that has the right number of bonds, 1, 2, 3, 4, and it's got a lone pair on top and 3 hydrogens hanging off of it. So that's what that looks like. And as far as my electronegativity, we're really just looking for the difference between the 2 of them. And here on figure 6.6 in your book, it'll give you all the electronegativities you need. Nitrogen is 3, Hydrogen is 2.1. So this is 3, 2.1, where the difference, is 0.9. And the electronegativities are also provided in your data table. And so then you just look at the scale, and whatever the difference in your electronegativity is, it'll tell you what kind of bond you have, whether you're ionic, polar covalent, or nonpolar. And here at 0.9, we're in the polar covalent. And dipole moments are a little bit tricky, but think about it like this. If you have a molecule that's not symmetrical and you have something that's polar, then you probably have a dipole moment. So for this ammonia, let me get this so you can see it. For this ammonia, the nitrogen is holding those electrons tighter than the hydrogens. So we have a little bit of polarity going towards the nitrogen from each of these. And because they're all pointed in the right direction, they're all pointed towards the nitrogen, you have a kind of overall lopsided amount of electrons that are on this side of the atom compared down to the hydrogens. One that would be different, for instance, if I have methane, which is the same geometry, and if that carbon is holding all of those more tightly than the hydrogens, then it's holding all of them, and it's symmetrical about that. So they're all pulling equally towards the middle, where this one, it's not pulling equally towards the middle. You have these hydrogens hanging off, but here they're everywhere. So this is symmetrical. There is no dipole. If it's not symmetrical and it's pulling, then yes, you do have a dipole moment. And it's polar because it told us it was polar from the polar covalent bond. Okay, your activity 4 continues a little bit on this table, but it's really just a matter of finding the difference in the electronegativities and what that bond means. So that should be pretty quick. And activity 5 is just do your best. I'm going to be pretty lenient on the grading for that. It is organic chemistry, but let me just note to you guys that you can make double bonds with what you're doing here. Let's see if I can set this up so you can see. You can create a double bond here. There we go. So you can make this into a big chain if you're trying to get a really great spatial representation of what those mean. But again, just do your best on activity 5. Okay, and call or email me if you have questions. My phone number is posted. Okay, good luck.